Good afternoon, everybody. So, quick show of hands. How many of you are here for the first time at Java 1? Yeah, this is amazing. I saw this in another presentation as well. Like a lot of first-time people here. That's great. Well, welcome to Java 1. I've been coming to Java 1 since the second Java 1 because I couldn't get into the first. Any of you go to the first Java 1? All right. I didn't see any hands. But yeah, it was completely sold out. They had no idea that this thing for programming doorknobs would take off, and that was the original joke with Oak, which was the precursor for Java. They had no idea how much the demand would be, and it just took off. It was an incredibly successful language and platform. As hopefully you're seeing this week, there's a lot of stuff going on in Java. I work for Oracle, but Oracle obviously bought Sun, but a lot of the stuff going on in Java is happening outside of Oracle too. Thanks to OpenJDK, the transparency work we're doing in the JCP, and things like that. So let me just start with, because I am required no matter what I talk about to put this legal disclaimer in, although I'm not talking about futures of specific products. But this is a statement that says, if I talk about anything in the future, please don't hold me to any of it. So, there you go. Let's see. So, my name's Cameron Purdy, and I was, years ago, at a startup called Tangasol, where we created a product called Coherence, which is one of the first, if not the first, in-memory data grid products. Now there are probably about 50 products in this space, some open source, some commercial. Incredibly exciting area in the industry. Distributed computing is a lot of fun. So how many of you work with distributed computing today? Makes sense why you'd be here. How many of you just think it's really interesting? So it is actually a lot of fun. And so my background, I'm not a computer scientist. I actually studied economics and political science, which is one of my honors roommates. I was talking to him the other day, and you know what he asked me? He said, "You want fries with that?" In other words, it's a fairly useless set of degrees. But I love software. I got into software company when I was in school, and been doing it ever since. And it's certainly a great field in terms, sky's the limit in terms of, we're creating things that people never imagined, even 20 years ago. So I joined Oracle in 2007, and been here ever since. So, quick overview of the agenda. We're going to take a look back, and then look back through kind of evolution, and a lot of what I'm going to be talking about today is going to be colored from my own experience. I'll try to keep this, kind of vendor neutral or something. I'm not going to, talk a whole bunch about specific product features or something like that. But I'm certainly going to explain it from what I saw in terms of the industry. And by the way, I'd like to put a special thanks. I don't know if he's here, but Rob Misick actually was kind enough to help put this deck together for me. So. Thank you, Rob, if you're listening. So we're going to take a look back through the evolution. How did this thing called in-memory data grids, how did these come to be? Also going to look at, good to see you. By the way, congratulations on your release. Speaking of data grids, we're going to look at some of the core concepts, like what makes this work, why did we choose the things we do, and these are core concepts that are incredibly useful regardless of whether you're building a data grid or using a data grid or even none of the above. If you're just building systems that have to scale and should be highly available. And understanding why those trade-offs are difficult and how to maximize what you can achieve in a scale-out environment. And then take a look at kind of where we are now, and hopefully a brief look of what's coming as well. So, Brief History of Time, of course, is a play on the book of the same name by, what is that famous scientist's name? Stephen Hawking, yes. So we started, if you go all the way back to, say, 1999 era, J2EE, back when it was called J2EE before Java EE, was just coming out. It was a huge specification. I read the whole thing, didn't understand any of it. What you had was a couple early application servers, most notably WebLogic, certainly still exists today. It was probably the most popular at the time. But there were other ones as well. Kiva, I think they got bought by Sun. And NetDynamics, I think, was another one. There were several very popular ones that you probably haven't heard of because they disappeared fairly quickly. But what we saw was that Java EE was designed, Java J2EE at the time, was designed for a scale-out architecture. And the idea was, you put everything on a server, and then you have a second server, and a third server, and a fourth server, and you somehow load balance across those servers, and it would scale. It would scale beautifully. And of course, it did scale beautifully, unless you had data, right? If you had to, say, talk to a database. And the reason why is because the application server, every time you asked for a piece of data, it would just go to the database and get it. And and the granularity was so small that if you asked for 2 pieces of data, guess how many times you went to the database? Twice. And even more insulting is that if you only deployed one server, so say in the case of WebLogic at the time, if you deployed one server, everything ran really fast. You're like, oh, this is great. If I have more users, I'll add a second server. So you'd add a second server, and what would happen? It would run like a horribly maimed dog. It would just come to a complete halt. So you'd have 2 servers, and the database load would go from 3% to 100%. It doesn't make any sense. Why would 2 servers crush the database if only one server, left it alone? And the reason is because the app servers had with only one server running, they'd cache locally. They'd cache all that data in memory. So the EJB calls were really, really, really quick. Everything was really fast. And then as soon as you added a second server, you had to turn off that caching or you'd get data corruption. So you turn off the caching and everything, because every request now is going to the database. So instead of scaling really well, what people found was when they really needed it to scale, it didn't. And this is the, certainly for our company, this is where the opportunity came in. We were, at the time, a very small company, and we hadn't built a better mousetrap. We didn't know what kind of mousetrap we were building. And we just knew we were going to build something eventually. And we kept on seeing this problem with customers that we were working with, where they'd start to scale out and everything would grind to a halt. And, since we were doing consulting as what we called our keep the lights on strategy, in other words, don't go bankrupt, we figured someone has to have solved this, right? So we went to Google, and Google, please tell me, has anyone solved this problem? And of course, we didn't actually write the query that way, but we were looking for all sorts of words that would describe this problem. And all we found was companies having this problem. And no one had really solved it. And so this was back in 2000, 2001 timeframe. And this is when you first started seeing this concept called clustered caching. Well, actually, it was only called that because we called it that because there was no word for it. There was no marketing jingo for it. Sometimes, if you look way back, there's a distributed caching is a long time term that's been used. Since we didn't know anything about computer science, we didn't know to call it that, so we called it clustered caching. Because app servers like WebLogic called it clustering, which of course was also a horrible misuse of computer science terms. But when we came out with it, we thought, well, this is great. We could put the data in memory and keep it in sync across multiple servers, and then every time it needs data, it doesn't have to go to the database, it just grabs it out of memory. And this was great. What we did was we started with replication. So you'd stick some data in memory, and poof, it was there on every server. So if you had 2 servers, the data was in memory on 2 servers. If you had 10 servers, it was in memory on 10 servers. Now, at the time, does anyone remember like Java JVM 1 and 1.2 and so on? The GCs were horrible by today's standards. I mean, back then, you didn't have enough memory to actually run into that problem anyway because it was too expensive. So most VMs were running like maybe 64 megabytes. Server VMs, maybe 256 megabytes. Ooh, that was big. And a big server at the time was a Sun E450 or something like that. My memory's going, so if I get some of these facts wrong, please don't hold it against me. But a Sun E450 maxed out at 4 gigs of RAM. Like I've got 4 gigs of RAM on my phone, I think. I mean, just think about it. Like I'm lying, of course. But you know, it's not much memory by today's standards. But back then, that was the big server. That was an $80,000 machine, which seems almost ridiculous today. But you know, you weren't going to have a cache of 10 gigs because you could only have 4 gigs max. And by the way, you couldn't run a VM anywhere near that size. So you can see where replication starts to break down. Because if you're sticking everything in every server, you're limited by how much free space you can get in the heap, which is pretty small. So luckily, we had a meeting with a customer who basically said, well, we love your product, but it can't work because we've got to store like 10 times that much data. And we thought, well, how would we do that? And, well, actually, I mispredicted the slide, so ignore my previous statement. I'll come back to that. So you started to see things emerge around like replicated models and things like that, like session management. So HTTP session management is one of the things that in a clustered mode would allow an application server to have, for example, high availability, where you'd kill an app server, and none of the users knew. So what was really nice about this when we started seeing systems like this, so this was built into things like WebLogic. We built an implementation in our own product as well to do things like this, and there were several others. I think there was one done by SpiritSoft, which was another messaging startup at the time, and there was one by JBoss, by Bella Bon from JBoss, who wrote messaging library called JGroups. You know, so what was really nice about something like this was you could have an application deployed on 10 servers, and you'd have, you know, a tenth of the users on each server, and you'd kill a server accidentally, and you know, no impact to the users because the session information that they were relying on was replicated across multiple servers. Now, the really nice thing about this was it allowed companies to start using Java EE for pretty much for nonstop systems, where they would deploy an application to one server, start it back up, take the next server down, deploy it, and start it back up, and this is what we called a rolling upgrade. So you started to see how some of this in-memory technology was helping not just the performance aspect of it, but also helping on the availability side. So the way we solved the space problem was partitioning. And you've probably heard of the word sharding as well. Sharding and partitioning are interchangeable terms. I was actually reading a debate online this week on Quora in terms of what does sharding mean and what does partitioning mean. But like all marketing words, they mean, please buy my software. So hey, at least I'm honest. So what we did with partitioning is we said, okay, if we have 10 servers, let's just put 10% of the data on each one and find a way to do it, you know, as automatically as possible so you don't have to write code to figure out what data goes where. And the way we implemented it as well was we automatically backed the data up. So we'd put 10% on one server, and then we'd slice that 10% into 9 pieces and put each piece on a different server. So we'd basically, I guess it would be called like striping or something in RAID terms. We'd stripe it out. And so now you'd automatically route all requests to whichever of the 10 servers had the data you were looking for. And if you added an 11th server, it would automatically load balance all that data management, so it would kind of spread out or bring it in, contract in if you killed a server, things like that. So it was like automatic failover. And the nice thing about this was now you could not just put more data in, but it started to introduce new concepts. In fact, one of the greatest concepts of partitioning is what we call ownership. And what this means is that when you partition, when you split up the work or the state management or whatever it is across multiple servers, each server owns the responsibility for a slice of that data, for a partition of it. And by owning that responsibility, it means that you have a place, and we'll get into the details of what this means later, but you have a place to go to for ordered operations against something. And this is actually the hardest thing to scale. So by partitioning, if you have what we call definite ownership semantics, meaning at any given time there's at most one owner for a piece of information, by having that you can achieve order in a scale-out system. So think about a counter, for example. If I have to go from 0 to 1 to 2 to 3, it sounds really easy, except you know, if you're in a scale-out system, you have to use something like a mutex or a semaphore or something. So let's think about how we would do this. We'd like lock the piece of data so that no other server would mess with it. Then we'd go get the current value. We'd add one to it. We'd put it back in. Then we'd unlock it. When you have ownership, instead of instead of doing that, you can actually send an operation to the data and say, I'd like you to add 1 to that piece of value. And because it's owned somewhere definite inside the scale-out environment, all those commands, if you will, can be queued in a definite order by the owner. So it's completely transparent to the consumer of this, but all that information and all the operations against it are being managed in a very predictable manner, ensuring that it doesn't go from 0 to 2 or 0, 1, 1, 2 or something like that, so that you can achieve very, very predictable outcomes. Also, things like persistence. Because there's exactly one place where that data is owned, you can read and write from a database for that piece of data from that one place. You can read and write from disk for that piece of data. So you're assigning ownership, and by doing so, you have a definite location within a scale-out environment for performing certain types of operations. And so on top of this, you started to see an emergence of data management features. Things like, let me think of some good examples. So I gave the counter example, where we're not counter example, but the counter example. Public speaking is, it's always interesting to hear yourself talk and hear all the mistakes you make when you're doing this. But the counter is actually like data management. It's no longer, I'm not just caching data or reading data. Now I'm actually relying on that data to be correct. And so because you have a definite ownership within a scale-out environment, you can now start to send operations to where the data is to actually do mutating operations, save it to a database, things like that. And then this is where we started to see that line drawn between, people started to say, why is this called caching? I understand it's in memory, but what you're doing is more like data management than caching. So we had to make up a new marketing word so we could charge more money for the software. So we called it a data grid. And you think I'm joking, but actually that was serious. So we actually kind of, in our own company, we split our product into 2 editions. One was more for the caching use cases, and one was for the data management features. And then, then what we saw was, as companies were putting more and more information into these systems, and by now, by the way, there were probably a dozen vendors in this space. So let me name a few of them. You definitely don't want to use any of their stuff. Just come get ours. But companies like VMware bought a company called Gemstone. They have a Gemfire, I believe is the name of the product. Very, very popular product. Often is used, sold. Well, it's sold by the guys who do the Spring work at VMware. So very popular there. JBoss has a new data grid called InfiniSpan. There's let's see. Other data grid. Well, Cache is more of a caching than a data grid product, but it's also very popular. It was called the Easy Hibernate Cache. That's where the name came from. There's a product by IBM called, it used to be called Object Grid. I think it's now called Extreme Scale. So, yeah, that's another marketing name. And then there's other open source ones. There's Gigaspaces, yes, Gigaspaces, which is based on the Ginny distributed computing model. There's also another open source one that's still fairly young, but expanding. It's called Hazelcast. Any others? Terracotta. Terracotta. I wouldn't. So Terracotta is the Cache product, but I wouldn't consider it a data grid. But it's definitely a very strong, very popular distributed caching product, and they're probably moving more in that direction. So Greg Luck from who wrote Cache, is also a co-spec lead with us on JSR 107, which is the caching standard that is 10 years late. So as companies put more and more data into this, they suddenly had to have ways to get it out, right? So they've put all their crown jewels of their runtime systems into these fairly non-standard, or emerging standard, I'd like to think of it as. But they put all their data in, now they're like, well, how do I get it out? I have all these other things. So we started having to create ways to access that information. Started very early on with things like, C clients or .NET clients or Java clients to get in and out of the data. More recently, what we've seen is a move toward RESTful interfaces. And of course, I should have mentioned one other product, open source, Memcached, I'm sure you guys have heard of that, and there's a whole bunch of commercial offshoots from that as well. So Memcached, one of the cool things about Memcache is that it has clients built in Perl and C and C++ and Brain, and like various, as a language, never mind. So lots of different languages, so it's almost become a universal wire format for simple caching use cases because a number of products actually talk memcached, even though they're not memcached in the back. So memcached is a fully partitioned model. It's not highly available, and it's often not elastic in any way, but it is very popular because it has the right price, which is free. And so let's see, parallel processing. So once all that data was in there and you were able to get stuff in and out, what we started seeing emerging, and from a couple different perspectives as well, depending on the background of the product, was different ways of manipulating that data. Sometimes for what we think of today as like big data use cases where you're doing like data mining out of big data sets, aggregation, work like that. And sometimes, just queries, like running queries against that data, building an application using queries, things like that. And because everything was partitioned, it was possible to spread out the work across those partitions. Since every server was owning some slice of the data, instead of like going to one server and getting that data and going to another server and getting that data, you could send a command out in parallel and use the aggregate memory and compute capability of the scale-out environment to process the data. Oh, and speaking of scale-out environment, I just realized there's another company that makes a product, I think it's for .NET, called Scale-Out software. So aptly named. So there are definitely a lot of companies in the space now. And then we've seen more recently an emerging area called Nosql Databases. And so Nosql Databases fall into a couple different categories, but one of the most common categories that's used is what we call a key value store. And most of these data grid projects and products that I've been talking about are based on that key value concept. And in fact, the one I mentioned earlier, Gemfire, actually was evolved from a database. So it actually has a lot of kind of NoSQL roots long before there was a word NoSQL. So what you're seeing is kind of a merging in to general NoSQL part of the market of a lot of the technology used in in-memory data grids. All right. And lastly, we've started seeing the use cases expand beyond kind of a traditional in a data center use case. We've seen quite a few products now having ways of providing redundancy, geo-redundancy, or redundancy across multiple data centers, where the information, even though it's in memory, it's often considered business critical. So if they lose the power, like actual data gets lost sometimes, and so they want to have redundancy across multiple data centers. You might ask, why would someone store something in memory if it's that important? And the answer is, well, they wouldn't if they had a choice, right? If you need that level of throughput or latency for operations, then some of these solutions that you wouldn't traditionally consider become your only possible solution. So most of these solutions also provide, like I said earlier, persistence, so capability to store to disk or store to a database, and most of them also provide both synchronous and asynchronous options for persistence. So even though if you lose the power, you could lose data, you might only lose, the last smidgen of updates. So a relatively small impact, which for some applications is completely unacceptable, and for others is quite acceptable. So I want to look at some core concepts. And these are the ones I was talking about earlier where, I want you to think about, why these systems were built the way they were, why did they evolve the way they were, and how can you take these patterns and apply them to application development in general, things like scalability and high availability. So when we talk about scalability, like how do you achieve scalability? I'm not talking about scalability within a particular server. I'm talking about scalability that has to go beyond a server. And there's two aspects for this. The first aspect is you want to be answering the question as early as possible. Right? So for example, the most scalable way to build a web application is to push as much of it down to something like Akamai as possible. And the reason is that Akamai has done all the work of going around to every university, every ISP, every this, that, and the other thing that has a connection somewhere, and putting a server there, so that when you get on from home and the page you're requesting can come from Akamai, it doesn't go anywhere. Compare that to if you put one server somewhere and you put a website on it, and then everyone goes to that one server. You're using long paths, if you will, through the internet. So you're creating a scalability problem where if you can push it out to the edge or beyond, you're actually kind of solving the scalability problem before it ever exists. Now the problem is you can't do much easily with Akamai or solutions like that, content delivery networks. So they're great for static content, they're great for content that can be generally out of date, but even though they have features to support some dynamic stuff, it's diminishing returns. It gets much more complex for much less return. So then, what's the next way to solve scalability? Well, partition. And again, we talked about why this works for data, but partitioning in general says, I have to find some way that I can take anything that has to be done and break that set of things that have to be done up across multiple resources. Horizontal scalability, of course, is what we're talking about here. And once I spread out the ability to manage those things, I have to be able to balance my load across them, which is, of course, fulfilled by the role of a load balancer. What we're talking about here when we talk about partitioning is we're talking about designing applications for elasticity, being able to have an application that is capable in its design of being run in a scale-out environment. And in doing so, you may be building an application that runs fine on one server, but if you don't design it to scale out, it won't. Scalability isn't something you glue on to an application. It's not it's not something you tack on after you're done. So typically, you have to rewrite applications to make them scalable because you have to actually re-architect them. And then the last point here, I say only buy what you need. And what I mean here is that scalability is hugely expensive, particularly as you add qualities of service to scalability. So what I mean is if you want like data consistency, like absolute data consistency and absolute durability and transactionality and things like this, each one of these qualities of service comes with a big price tag, and I'm going to play liberties with math here, they're exponential, right? So if I pick one, it's not that expensive. But if I pick two and put them together, like I want transactionality and durability, all of a sudden those costs compound significantly. So why is that? Well, because the only thing that doesn't scale is data consistency. That is literally the only thing that doesn't scale. If you want something to be in order, it doesn't scale. If you want it to be, and by the way, because you can think of it kind of like a Turing machine concept, but in a distributed system, you can define all state management by messaging and all messaging by state management, which means things like, a little theoretical, I guess, but things like ordering and consistency of information are actually the same thing in a distributed system. And this happens to be the only thing that limits scalability in a distributed system. So when we talk about scalability and why it's hard, think about it this way. Like if I'm building a system and I just whip it up and throw it on a server and it runs really fast, kind of like the early example I gave of application servers, yeah, it's really fast. I've got RAM and I've got CPU. These things are fast, right? And then I start by adding something like persistence. Well, SSDs are pretty fast, but they're not like RAM. I have a spinning disk. Well, it's local. I've got aggregate I/O if I scale it out. Each server has its own local I/O, so it scales well. But by the time I start talking on the network, I've already lost, right? So I go asynchronous stuff on the network. Yeah, it scales pretty well. Or if I partition, meaning I'm using synchronous requests on the network, I can see the scalability dip a little more. And at the worst end of it, we see things that are centralized. which is, for example, a traditional database model. So why don't databases scale well? Well, because they're at the bottom of the list. Because they're centralized, because everyone has to go to one place to get the right answer. So, and by the way, it's interesting. If you think about, did I went to the wrong slide? No. Sorry, guys. What I was going to say is it's interesting if you think about databases, why they're hard to scale. It's because they start with an incredibly high quality of service. Like they guarantee, some sequence of transactions will take you from any previous state of the database to any current, state of the database. And that right there is what I was talking about earlier in terms of ordering. Anytime you have to guarantee ordering, you lose scalability. So, what about high availability? Something else that typically is needed by applications? Well, the idea behind high availability is really simple. Don't have any single points of failure. Like be able to shoot anything in your data center and not have the system go down. Well, it's pretty obvious. But how do you implement high availability? Well, let's look at 3 different ways. So the first way is to be stateless. If you don't have any state, you can cookie cutter deploy something that's stateless because you can send a request to any of them and it'll work the same way because it's stateless. It doesn't manage any state. Now the problem is with stateless things is they scale well because they put the load somewhere else, right? Because they're stateless, they delegate state management somewhere else. That's why stateless applications, which was such a great thing supposedly when Java EE came out originally, I just dumped all the load on the database. And even though it's tempting to consider it a conspiracy theory by a vendor that sold very large servers and a vendor that sold databases, Sun and Oracle, I think it was more just a reflection that something that worked well in academia didn't necessarily translate to the real world. So statelessness was considered, that's the up-and-coming thing in academia. But when they actually applied it in the real world, they realized all they were doing was moving the bottleneck to somewhere that was more expensive. Which, of course, is why Sun did so well and Oracle did so well at the time. Because everyone was buying giant Sun servers and putting Oracle on it. Let's see. So, stateless. How about cached? Why do I put cached here? Well, because high availability also means it's not just that the server's running. It's that it can answer a request within some period of time, right? So if I can cache data and I don't care if it's up to date, I can answer the request on that server without going somewhere else. So that makes the system intrinsically more highly available because each server that I'm sending load to can be caching information and servicing requests. And lastly, replication. So if I can't be stateless and if I can't deal with data consistency issues with caching, I have to have some way of replicating information. Now, the database replicates to disk. Makes sense, so that if you lose the database, i.e. the running process, you can always go to the backup, which is on disk itself. Now, what we're talking about in a scale-out environment is replication in memory, typically. These two things, though, it turns out they go together. It's kind of like peanut butter and jelly. So scalability and high availability end up often being both requirements of systems, but it turns out that they're actually solved in the same way. In other words, scale-out is redundancy. So if I'm scaling out a stateless server to handle more load, it turns out I'm also creating a system that's more highly available because it has multiple instances of those servers. Load balancing is failover. The fact that I can send a request somewhere and it makes sure that it gets to one of those servers that I've scaled out to, that means if one of them dies, it's going to make sure that the next request goes somewhere else to another server. And geo-distribution is, again, it's a form of scalability across geographies and a form of high availability. So stateless, like I said, it's always HA. Cached, it's HA if I can tolerate the consistency. And the only thing that's really challenging here is replication, state management. And the reason is because, first of all, you have to partition it. Right? That's the only way you can scale state management, is to partition it. And secondly, synchronous replication, particularly over a wide area network, is hard. So why don't we talk about performance? Like, why are we talking about scalability? I mean, isn't what we're actually after is something that performs well? And the answer is that performance is the red herring, right? I remember early on there'd be, you know, companies with disastrous problems with their web applications, and they'd have an engineer, oh, let's profile it, right? Well, look, you could make the code 100 times faster and have no impact on performance. Because what you're doing in profiling is you're looking at, you know, a single thread going through that system. The real problem, the reason it looks like it's performing badly is because it's not scaling. Okay? If it scales, then, you know, the 1,000th user gets the same, you know, the same performance as the first user. Okay, so if the first user has poor performance, then you start profiling, right? But the real thing you have to focus on is scalability, because it's something that has to be intrinsically designed into an application's architecture. It's not something you can add later. While performance, if you go back to, what was the guy in the Navy that said the root of, wasn't it the Navy, the root of all evil is premature optimization or something like that? Who said that? Was it Donald Knuth or? All right. I'm not sure. Knuth? Okay, so the root of all evil is premature optimization. So solving scalability first lets you later try to address things like performance. So what we talk about is scalable performance, not performance. Scalable performance is knowing that, basically, if you boil it down, it's a concept that says, look, if I can achieve this much with one server, and I add another server, and another server, and another server, I want my third server, and my fifth server, and my 500th server to be providing the same amount of throughput, and from an end user point of view, the same latency on requests. So basically it says I'm going to design systems such that as I add resources, I've designed the systems so that as I add the resources, I understand how those resources are going to translate to additional throughput. Right? And that's why partitioning is absolutely essential. So let's talk about where are we now. So what's going on with this part of the market today? Well, it was a very rapidly changing field for a number of years. I mean, this was probably one of the most competitive areas in the industry. Like I said, there's a lot of different products and open source projects attacking this area. And so what you saw for years was that, you know, the features were coming so fast and furious that you know, products generally didn't keep up on some of the other aspects of what it means to be a product, like being able to manage and monitor it. You know, we had entire new classes of problems that we had never faced before. Like, you know, you have one server generating a gigabyte of log a day. Well, what if you're running 1,000 servers? Right now, you say, okay, mail me the logs. We've literally had, you know, customers send us hundreds of gigabytes for one log dump. Like, wow, thanks. What do I do with this? So, you know, you've actually seen companies emerge around these problem sets, like Splunk. I don't know if you've heard of them. You know, they do log mining across multiple servers and things like that. Integration, like how do you plug in other things with these technologies? Because early on, you know, these technologies were used as kind of point solutions to solve some problem that no one else could solve in a conventional way, so to speak. Or the alternative is that people just found the technology so interesting that they plugged it in even though they didn't need it. We've seen a few of those. But generally speaking, I mean, these were technologies being used to solve very hard problems. But, you know, after it was in place, you know, what about the next generation of developers coming along that have to plug into it, and you know, products that have to work together around information? You know, that's high velocity information and typically massive data sets. And an area that we're investing in quite significantly in our own products is this concept of engineered systems. So making sure that the hardware and the software are optimally designed for each other. So I'll just give one quick example there. You know, we've been working a lot on low-level messaging. Anybody know about 0MQ? Just ring a bell. 1, 2, 3. Excellent. It's a C library for very low-level messaging. There are other products in this, or products in the space. But if you think about it, the first thing you do as you're building distributed systems, whether it's something like this or something else, is the first thing you do is you create messaging so that you can do message passing as a basis for building basically distributed state machines. And you look at, okay, so I need to do messaging. So what do I have in Java to do messaging with? Well, JMS. Well, that's, I hate to say, it's not low level. JMS may be hard sometimes, but it's certainly not low level. It's fairly heavyweight. So what you need as an infrastructure, common infrastructure for all distributed systems, is some form of very low level messaging. I mentioned JGroups earlier by Bella Bon, who's with JBoss, a very popular one, and there's others. But what we've done is we've actually created new APIs that we hope to eventually push into Java explicitly for low-level messaging. And these are asynchronous APIs, meaning the API itself is asynchronous, not just asynchronous messaging. So on our Exalogic hardware, we now have reliable delivery, and I'm not going to give exact numbers, but well under 10 microseconds. Reliable delivery, and those are 4K payloads, under 10 microseconds. So Java, I expect Java to become, as it has in many other areas, I expect it to become one of the go-to platforms for low latency systems. In fact, I can't give any names for NDA reasons, but the largest, most successful financial services company in low latency, actually all their work is done in Java already, and they've built their own InfiniBand-based software for doing this. So it's just funny, 5 years ago you wouldn't have thought of Java as being the low latency language, but today it is. I mean, it is basically, I'm seeing it everywhere, and hopefully we'll have this coming into the JDK before too long. So that's a...
Which feature you talk about that is in the messaging with the language?
So which technology am I talking about? So I'm talking about InfiniBand-based messaging.
That's part of Java?
Not part of Java yet. It's something that we're going to propose to become part of Java.
Okay. So that's, okay, right now it's just its own product that the Oracle has?
So the question is this something that's a product that Oracle has? Today it's not actually a product. It's kind of baked into a couple things that we have today, but we're trying to prepare it so it'll be separable from Oracle products, and we can push the technology actually into the JDK. So first we got to prove it out that everything works and we love it, and then once we're perfectly happy with it, then we'll push it out as a proposal for Java. And that's by the way, that's also in terms of throughput, we're actually limited only by the hardware bus in the servers. So we're actually pushing data so fast that the only thing limiting data flow is the actual backplane of the server, the PCIe bus. So we're over 30 gigabits per second sustained throughput. Pretty crazy. All right, let's take another look at it. So what are the things coming up and around this technology? So first of all, I'm pleased to announce, if you haven't already heard, that JSR 107, which I'm a spec lead for, and I should have finished 10 years ago, it's finally coming to fruition and will be in Java EE 7. And I will tell you, my experience with this is that it's really hard to do a JSR from start to finish. It's a lot of work. So I hope you guys are willing to pitch in. Obviously, the JCP is the Java community process, and it's free to join. While Oracle definitely contributes quite a lot to the development of Java, this is it's also a platform that's shared across the industry. So we certainly welcome the involvement of the community, and we've been working very hard to add transparency. We actually have the first step in the transparency process, which was JSR 248, I think. So that's done. So now all of the work going on in expert groups is public, if they've adopted the latest version of the JCP. And we have the second phase already underway in terms of the transparency project. So, also the InfiniSpan guys from JBoss, led by Monique Sertani, started a new JSR as well, based on InfiniSpan. So they're looking at standardizing some APIs for data grids. I'm not actually aware of the current status of that project, so I can't really comment on it other than the fact that it does exist. Another exciting area of development. NoSQL, like I said earlier, a lot of the concepts in NoSQL actually came out of this space, and you're seeing definitely some blurring of lines. I won't go into too many details there, but a lot of the times NoSQL is being used for caching, so in-memory data grids are obviously ideal for that. And a number of them have already also added or already had disk-based persistence as well for the data grids. So even though they're running in memory, they're fully durable as well. Big data is another area that we've seen a couple vendors focus on recently. So big data is a little bit hard to define because, like a lot of other terms that we use, it's a marketing word. So it gets VC money, but it doesn't necessarily translate to the real world. So sometimes big data means a gigabyte. Sometimes big data means a petabyte. And there's a big difference between a gigabyte and a petabyte, at least 4 letters, and 6 orders of magnitude, if I understand correctly, or 9. I don't know. Math wasn't a strong suit for me. So when we talk about big data, we're not necessarily talking about the size of the data as we are talking about what we're trying to do with it. And basically, concepts behind big data are, how do I go through lots of data very quickly? How do I scale out the processing of data sets? So big data might only be working with 10 terabytes, and so by your definition, that might be tiny data, or it might be huge data. But it's not so much how much data you have, but it's how you go after it. So things like MapReduce, for example. So a number of products have MapReduce functionality in them now in the data grid space. Parallel execution and things like that. And then lastly, cloud. So cloud is actually a culmination of, when we talk about cloud computing, it's actually a culmination of many things that we've been trying to do for years in our industry, which is the democratization of the data center. How do I take the resources in the data center and make it available when needed to the people who would provide value to my business by having those resources? So traditionally, that meant going through IT. I need a server. Okay, I'll order one. It'll be 9 months. Actually, at Oracle, it takes longer than that. It's probably 15 months from the time that I need a server to the time I get it, unless it's an emergency. So on the other hand, I go to Amazon and I have a server in 12 seconds. That's the democratization of the data center. And if you can tie that concept in with supply and demand, if you will, if for example it's charged to you when you have it, like Amazon does, of course, because they make money on it, then you're not going to be wasting it. Like if you look in a typical data center, most of the servers are doing nothing. They're literally, the utilization, depending on the study you read, is somewhere between 1% and 2%. They're just burning dinosaurs. That is wasting electricity. So what cloud is about is finding a way to turn the resources of our data centers into rationally consumed resources, and by pushing these resources out as self-service, for example, infrastructure as a service. But within the cloud, it creates new requirements, and one of those is that I want to be able to build applications that I can deploy into a cloud environment, and then I want to go home and sleep. I don't want to be like monitoring a dashboard for my system. If I need more throughput, if I have more user requests than I expected, I'd like it to start up another server and another server and another server. I'd like it to scale out. And so what you see is that the concepts that we talked about today are absolutely essential for this type of system, because every application should be built from the ground up with these things in mind. When I say every application, I'm not talking about what you play on your iPhone. I'm talking about what sits back on the server. So every server-side application should be built from the ground up to be scalable and to be highly available. Because I don't know about you, but I very rarely meet any application developers who are building something that isn't considered, at least by them, to be mission critical, require high availability, and they'd like to believe it's going to be so successful that it's going to have lots of servers too. Right? So anyone here not build applications that need high availability and scalability? So either everyone's too embarrassed to admit it, or it's true that you'd like to have high availability and scalability. So when you think about how we're pushing these things, for example, into the standards process and things like that, what we're trying to do is we're trying to take these things that used to take rocket scientists to build, and we're trying to democratize them as well. If we can build them into the standards such that they're easy to consume, so that you get these things not for free, but by understanding, common design patterns and the APIs in the platform itself, that you'll be able to build every application from the ground up such that it can scale and it can be highly available. So that's why I think this is a pretty exciting area. Obviously, I have a preferred implementation of all this because I helped to build one, but it's still an incredibly exciting field with just so many things going on every day. It seems there's new inventions and new approaches to solving these problems. So. Just a little bit of look in terms of some of the areas that we see emerging. So let's see. I don't want to talk about some of these. One of the projects that we're doing is called Elastic Fabric. None of this is visible yet, but it's a concept that everything that we've learned in terms of distributed computing and how to make things reliable and scale well is that basically the network is not your friend. Like everything that works well doesn't work on the network. In fact, the network only works when you're developing. If you put something in production, it always fails. The network's unpredictable. The machines are there's so many unpredictable things. It's like trying to build a house on top of a bunch of lily pads. Everything's moving up and down. It's like you're sinking. The network's very unpredictable. How do you build a stable platform in a distributed system so you could build on top of it, right? And the answer is really simple, actually. It's a concept of a state machine. Like if you want to eliminate edge conditions in software, go back to Computer Science 101, which is as far as I got, and you'll see there's this concept of a state machine. Like I have a state, you ask me to do something, I have a new state, right? And no matter how many times, if I had that state and you asked me the same thing, I'd end up in that new state. It's like there's a predictability to it. It eliminates edge conditions by design. Right? And these concepts are built on ordered messaging and state machine concept. And there's a number I've been trying to read myself to educate myself on some of these topics. What's been done in academia in the past on all these topics, and there are a number of papers on this quite interesting. So when we talk about Elastic Fabric, what we're talking about is how do we push down all these things that we learned about how to build stateful, scalable architectures? How do we push them down so that they just become natural parts of everything that we do? And basically what that means is, having, I already talked about it, low-level messaging support in Java. And on top of that, having that concept of being able to have scalable, scale-out, partitionable state machines as well. So that's something that we're also designing. We see a lot of use cases around what we call XML, I don't know if I call them XML processing grids, but XML grids. So grids where I'm trying to take all this data and make it consumable. In fact, more recently we've seen a move toward RESTful interfaces, XML and JSON now, particularly with a push toward HTML5. How do I make this information, be able to push all the way down to a browser client? And how do I make the information consumable by any language or any client? And then, from a management perspective, moving much more toward autonomic computing. So fully lights out, computers that manage themselves. So I've always wanted to have a project named Skynet to do something like this. But you can imagine that, that's what we are trying to build. We're trying to take things that we used to have to do by hand and push them down into what we think of traditionally as an operating system. I don't know if any of you did programming years ago with multi-threading or symmetric multi-processing back before we had things like synchronized keyword in Java or something like that. And it was really hard, right? And in fact, back before there were threads, how did you do multi-process. You know, if you had two CPUs, SMP, what were the, if you didn't have a thread as a concept, how did you do SMP? And, you know, these things, they just seem obvious now. It's like, well, yeah, we have threads and we have atomics and we have transactional memory and we have, you know, synchronized keyword in Java and all this stuff. Like, so we've pushed down into the platform all these things. So when we talk about, you know, multi-servers, how is that different from multi-threads? Right? We think, oh, big deal, I have 100 servers today. Well, you don't say, big deal, I have 100 threads today. But when's the last time you had an app server that had less than 100 threads running? I mean, well, don't answer that question, you probably have. But there are, you know, quite often you look at a server and it's got hundreds and hundreds of threads running. And you don't think anything about that now, but that was huge 10 years ago. So how 10 years from now, how can we look back and say, oh, remember I used to brag I had a clustered system? Like, the word cluster should go away because it should just be the normal, right? Scale out should be the normal. Elasticity and dynamic elasticity should be the new normal. You know, so to do that, yes, we need innovation in the platform and everything else, but we also have to drive it down and make these things just absolutely bog standard, where every application we build looks like this. And by the way, then you will be able to sleep a lot better at night because, you know, you get unexpected load, you get unexpected outages. You know, your systems are going to just keep running, and that's what our job is. Our job, in some sense, is to obsolete ourselves, but not because we're trying to put ourselves out of a job, but because there's going to be something even more exciting over the next hill, some next problem that we're going to have to solve. All right, and with that, I'd like to just say thank you. There's some other sessions of interest, perhaps, so I'll put that up there. But thank you very much. I don't know how we're doing on time, but if we do have any time, I'd be glad to take some questions. So you had a question?
So now you have the caching and the NoSQL. They are kind of performing the similar purpose.
Yes.
How would you choose one versus the other?
So the question is, you have caching and you have NoSQL, and they're performing the same purpose. How do you choose one or the other? So the answer is pretty simple, which is, you know, every one of these products or solutions has a sweet spot for what it's trying to solve. So you want to look for something that has a sweet spot that matches what your problems are, because basically it's like Turing complete. You could use any one of these products for any problem, right? Golden hammer approach. But you know, you're going to end up with something that's quite suboptimal. So look for the types of products that are built to solve the problems that you're facing specifically. That's what they specialize in. And then within that, regardless of if they call it a data grid or NoSQL or NewSQL or NextSQL or, I mean, there's all sorts of big data. Who cares what they call it? Is the problem set that it's focused on solving the problem set that you're facing? You know, narrow down the list to a small number of solutions and then evaluate them, see how they actually apply to the problems that you have in your domain. So, and it's, like I said, it's a very rich field. So there are many, many products out there. So it's almost guaranteed that no matter what your problem domain is, there's at least 2 or 3 products focused on solving your problem.
Can we get the slide?
Excuse me?
Can we get the slide?
Can you get the slides? They're going to be posted, right?
What, I'm sorry, where do we get the slide?
His slides are going to be posted on Oracle's website.
Okay, so the slides will be posted on the Oracle website. Okay. And that's the same place that they're posting all the Java 1 content, right? Okay.
We only got 1 minute.
1 minute.
You're dealing with an existing system that's able to large amounts of data, using the database, trying to migrate. What are some of the mechanisms of qualities by looking at the data? You said managing the data is more important than size of the data. What are some of the mechanisms that you take a look at the data and then try to pull out stuff that you
So if you already have everything in a database and you want to, if you will, refactor, re-architect around it to start to bring some of that out, how would you do it? Well, applications tend to fall into 2 general categories, so I'll try to answer this from a fairly high level because it's easier. As you know, every application is going to be challenging in its own way. But generally, applications go after data by in a relational manner, or it goes after it in an object manner. So if you look at an application, is it using Hibernate? Is it using TopLink or Eclipse Link, JPA, Kodo, JDO, one of these products? If so, what it means is the application already has a layer in it that's designed to bring the relational model abstracted up into an object model. And in that case, it's actually fairly easy to adopt technology like NoSQL or a data grid or distributed cache, because the information is already being managed in a granular form that at an object granularity. On the other hand, if you open up the application, you start looking, you're like, oh, this JSP has some SQL pasted in it, and this one has some SQL pasted in it. That's a bad sign. That means that basically you're going to have to change every component in the application because they're all going directly against the database, right? So it's a very wide front, if you want to think of it in the military. You know, it's one man deep and it's, you know, 50 miles long. So that, when you see that, you're probably in trouble. And there are certainly solutions in that space as well. How do you accelerate database connectivity? How do you shard databases, et cetera? But if you're looking to adopt this type of technology and you find SQL sprinkled all over, you're in trouble.
Does Oracle, when I say Oracle on the database side, do they have any, are they focusing on doing that as well?
So is Oracle focused on doing that as well within the database group? Absolutely. So they have a couple different solutions for this. They have a ×10 database, which is an in-memory database. It's lickety split fast. There's also solutions from like IBM and others as well in the in-memory database space. Oracle's probably #1 answer for this is RAC and Exadata, which is an engineered system built around RAC and custom hardware. It's hugely expensive. It's a very high margin product because there just isn't any competition in the massive. Like if you look at the numbers of transactions, I don't have them offhand, but I've seen slide presentations on Exadata. It's like, how many million transactions per second? Like, it's amazing. But yes, it is expensive. And that's the reason you want to design for scalability, because you don't want to get trapped where your only answer to get out of the scalability problem that you're in is to buy some, $10 million machine. Although Oracle will be glad to sell you one. So, with 22% maintenance. All right, so thank you very much.